Okay, now that we've talked about all the conditions for doing a confidence interval or a significance test with the slope of a regression line, we're going to go ahead and start talking about the standard error of the slope. And our standard error really comes from that standard deviation of the population, but we don't really know the standard deviation of the population, so we alter that based on the information that we have. And so our standard error right here is SE, so standard error, and the little b is for slope, equals S. And so this S is really the S here, the lowercase s, which is the standard deviation of our residuals. And that will be divided by the standard deviation of our x values, so the standard deviation of our x variable, and n is our sample size. So we're going to use this to help calculate our information. So what's weird here is that if we're doing all of this on our own by hand without a computer output, we have to calculate S, we have to calculate SX, and then we use that to calculate our standard error. So it's quite a bit of work. We'll actually go through two examples, one where we have a computer output and one where we'll have to calculate on our own to figure out how that works. So the next part is, how do we interpret this? So we interpret standard error of slope by how far we expect our slope estimate to be from the truth in repeated random sampling or repeated random assignment. And then the substitution of S for our original standard deviation causes our distribution to become a t-distribution with a degree of freedom of n minus 2. So this is the first time we've seen a degree of freedom of n minus 2. We've always used kind of an n minus 1 idea. And now we're beefing it up to n minus 2 based on our regression formula. Okay, so confidence intervals. So today we're talking about confidence intervals. Tomorrow we're talking about significance tests. So we have our state. We will estimate the true slope beta of the population regression line relating blank to blank. Usually this should be our y value to our x value, also known as our response to our explanatory, at a confidence level, making sure that we state at the beginning what our confidence level is. And then we go to our conditions. So our linear condition, remember scatter plot looks linear or residual plot shows no pattern. And then we have our random condition where we have a random sample of size n, or we have size n in a random experiment. And then we have our normal condition where we create a histogram, box plot, normal probability plot on the calculator. We're looking for skewness or outliers. Make sure that you're drawing this on your paper so they can tell. Then we have equal variance, so we look at the residual plot. We're looking for scatter above and below and right and left. And then, of course, we have our independence condition. So after we've checked all of those, we go through and we perform our calculations. So the very first thing we do is we put our information in our lists, and then we go ahead and calculate our regression on the calculator. So this is going to be a calculate lin reg, and then we always do a plus bx on our calculator. We write it in that form because that's what we do in stats. And then, so then we're going to find the slope of the regression line. So we're going to look for that b value. Then we're going to do a one variable stats of our x list that allow us to find sx. Then we're going to calculate s, which requires us using the residuals. And we can only do that after we've calculated linear regression. And then we're going to use these pieces to calculate our standard error. This is only done if we don't already have a regression output. From there, we calculate our t star. We do an inverse t, remembering that our degrees of freedom is n minus 2. And then we compute the interval as shown. And then we interpret our results. We are blank confident that the interval from blank to blank captures the actual slope, so on and so forth. So, sample problem. We've talked about the the conditions before. This was relating rows to test score, so if you sit closer, will your test score actually be higher? And we actually have a computer output. And so we're going to use this computer output to help us out, and you'll see that this is much easier. So just a little reminder to you of where information is from our computer output. So the first thing we're going to go ahead and start off with is state the equation of the least squares regression line. So the first thing I need is I'm going to have a y hat equals, and then we're going to have our y-intercept. So here's our y-intercept. So y equals 85.706. And then we're going to have our slope, and this is our slope. So minus 1.1171 x. And so there's the equation of our least squares regression line. Now define any variables we use. Typically when we define variables, we're going to go ahead and say, well, our y value is really our test score. So my predicted test score, so we put the hat on it for predicted, equals 85.706 minus 1.1171, and our x value is really our row number. And so now we've written our regression line with our variables inside of there. Now identify the standard error of our slope. So the nice thing here is that we already have SE coefficient. And since we're doing the standard error of our slope, we go down to the slope line, and that is our standard error. So 0.9472. And that's really just interpreted as after many trials or many repeated samplings, our slope on average will be 0.9472 from the true slope. And so again, just interpreting, what does that mean? So now we're going to calculate the 95% confidence interval for the true slope and show your work. So we will estimate the true slope beta of the population regression line relating row number to test score at a 95% confidence level. Use t-interval for slope. So again, we're using t-intervals for these. We already checked the conditions earlier in our notes, so now we're just going to go ahead and run to our do. So in our do part, we need a little bit of information. We already calculated our slope, which our slope was negative 1.1171. And then we found our standard error of our slope from our printout, which was 0.9472. So these were those numbers we're looking for, slope and standard error. And now all we need is a t-star. So our t-star are our critical value. We're going to calculate with an inverse t. And with our inverse t, our area is, so if it's a 95% confidence, we have 5% left over, and we want half, so 2.5%. And our degrees of freedom is our sample size minus 2. And our sample size happened to be 30, so this is going to be 30 minus 2. And so this is going to give me a t-star value of 2.048 approximately. And now we put that together for our interval. So for our interval, we're going to go ahead and take the negative 1.1171. We're going to plus or minus that t-star, and then times by that standard error. And so now once we calculate that, we're going to get an interval of negative 3.057 for the lower bound and 1.82816 for the upper bound. And so now we can go ahead and say we are 95% confident that the interval from negative 3 to 1.8 captures the actual slope B of the population regression relating row number to test score. And so again, this was really simple because they gave us this beautiful computer printout, which we like to have. But sometimes it's not going to be that easy. So here's our next one. I recommend pausing and writing down everything that's on here and then coming back and let me talk about it. And I'm going to do a lot of going back and forth between this and the calculator so you can see how things are calculated. So for their second semester project, 2 EP Stat students decided to investigate the effect of sugar on the life of cut flowers. They went to a local grocery store and randomly selected 12 carnations. All the carnations seemed equally healthy when they were selected. When they got home, the students prepared 12 identical vases with exactly the same amount of water in each vase. So they put 1 tablespoon of sugar in 3 vases. In the next 3, they put 2 tablespoons of sugar. In the next 3, they put 3 tablespoons of sugar. In the last 3, they put no sugar. After the vases were prepared and placed in the same location, students randomly assigned 1 flower to each vase and observed how many hours each flower continued to look fresh. And so we have the data listed. So what you're going to want to do is you're going to want to put this into your calculator under L1, this in your calculator under L2, and then you're going to want to go ahead and graph the scatter plot. So we're going to go ahead and take a look at our calculator. So here's my calculator, and I'm going to go to Stat and Edit, and so there's my L1 and there's my L2. So if I want to go ahead and graph this, I'm going to go ahead and do a second stat plot. I'm going to go to a scatter plot, which is our first option, and we're going to do list 1 and list 2. So second 1, second 2, that gives me my lists. And then I'm going to make sure I have no equations in there. There we go. And I'm going to graph it. And I'm not seeing anything, so I'm going to zoom 9. And that allows me to see that graph. And so now I can go ahead and I can sketch that out on my paper. Well, now you can kind of tell, here I have 2 dots. This one I only have 1 dot. Why is that? Because I noticed that I had 1, 204 twice, so there's really 2 dots there. So I drew it like that so I could see that even though on my graph it looks like 1 dot, there's really 2 dots there. So I look at that, it's pretty linear, but we want to look at the residual plot to see if it truly is linear. So how do we do the residual plot? Well, to be able to do the residual plot, you first have to be able to do the least squares regression. Whoops, sorry about that. So we're going to come back to here. I'm going to go ahead and stat calculate. I'm going to go down to linear regression. I'm going to do my linear regression between L1 and L2. And I'm going to store my regression because I want to be able to have access to that in my calculator. So I'm going to hit alpha trace. I'm going to program it in there. And so now I get that regression. So I get my y-intercept, my slope, I get my r squared, the coefficient of determination, and then I get my correlation, which is a pretty good correlation. And then if I wanted to graph, I can see that regression line with my scatter plot. But now that I've done that, I actually have access to my residual list. So now I can go to second stat plot, and I can actually do a scatter plot with my x values and the residuals. So how do I get my residual list? Well, I go second stat, that's the list. I'm going to come down to residuals. And so it'll graph that residual on my y-axis. So now I can hit graph. I'm going to go ahead and turn off that line real quick. Okay, so now graph, and I can't see it, so I'm going to zoom 9. And now I see that residual. So I can look for the scatter and all that. It seems like there's a little bit of a pattern. I might be a little worried about that. So when I go do my residuals later, I'm going to want to take a look at my histogram or box plot and all that to see, should I be concerned? So then we graph that right here. And so that looks pretty similar to what we were seeing. And now what we want to do is we want to go ahead and do that box plot histogram normal probability plot. So I went ahead and did a histogram because honestly, if you're going to do one by hand, the histogram's actually pretty easy. But I'm going to show you all of them on the calculator. So now that we have the residuals, the residual plot, we're going to go ahead and we're going to do a histogram. So we're going to do a histogram of our residuals. So I need to go back and get that residual list. And then I'm going to graph it. And I'm going to go ahead and zoom 9. And so we can kind of see what that looks like. So it looks a little weird, not entirely symmetrical, not entirely normal. So you may want to check your box plot. So I can go back up here and now I can go ahead and change this to a modified box plot. Graph it. Zoom 9 it. So yep, we can tell there's no outliers. We can tell there's some skewness. Should we be worried? Well, if you're not sure, let's go ahead and check the normal probability plot, which is by far my favorite for checking for normal. So the very last one, we're going to go ahead and do that. And we're going to use our data list of residuals on the axis X. So we're, again, just graphing the residuals. So graph, we're going to zoom 9. And so we can kind of tell it looks pretty straight. Where we're starting to get that skewness is that little clumping right here. But overall, that looks pretty darn straight. So I would say it's close enough. The skewness isn't going to affect it enough that it's not that big of a deal. So being able to go through that is really, really helpful for us. And so now we have all those bits and pieces. Once we have all those graphs, now we can go through and we can calculate the little bits and pieces that we need. So now we're going to go to our test. So we're going to construct and interpret a 99% confidence interval for the slope of the true regression line that is going to relate sugar amount to flower freshness. So checking our stuff, linear, we show a moderately linear association. The residual plot shows no obvious pattern or curvature. We had a random assignment of bases. The histogram shows no strong skewness or outliers. Again, I double checked that with that normal probability plot. We have equal variance. Our scatter is pretty even. And we have random assignment, which assures our independence. So now we have to get to all of our bits and pieces that we have to calculate by hand. So we need to find our standard deviation of our X. We need to find the standard deviation of our residuals. So there's a couple things I wanted to point out to you. To find little s, we're going to come back to here, and I want to point out to you how we calculate s. So we're going to be using this idea to calculate s. So let's look at our calculator and find the bits and pieces of what we need to know. So here what we're going to do, we're going to quit that, and we're going to find our standard deviation of x. So I'm going to calculate the one variable stats of my L1, and this gives me the standard deviation of my x values. So I'm going to use that to find standard error, and the next thing I need to find is s. So the first thing I need to do now is I need to go back into my lists, and you know how we graphed with our residuals? Well, we can graph with residuals, but we can't calculate with residuals. So I'm going to put the residuals into a list. So now I can go ahead and calculate with those values. So I'm going up to L3, and I'm going to go ahead and put my residual list into L3, which is nice because now I can look at all those different residual values, and I can see what's happening. So now that I have a residual list in L3, I can now go ahead to calculate one variable stats on that L3. And unfortunately, I can't do the standard deviation of L3 because that standard deviation formula is wrong. Well, not wrong, but it's wrong for our purposes. To calculate little s, I need to divide by n minus 2, and this standard deviation formula uses n minus 1. So what I need instead of this is the summation of my x squared. So I need that 566.4. So now we've grabbed two values that we really need, and we're going to use that 566.4 right up here. So now I'm going to go back. We're going to write down all the different things that we need. I gotta get away from my camera where I use that calculator. I need my pen. Okay, so we found the standard deviation of our x to be 1.168. Now, to find little s, I needed that summation of the residuals squared, which was at 566.4. And what I'm going to do is I'm going to divide it by n minus 2. So I had 12 carnations minus 2, and this is going to give me an s value of 7.53. Really close to the standard deviation that the calculator gave us, but off a little bit. The calculator gave us 7.175. So it's going to be off just enough that everything else will be thrown off. So now that we have those bits and pieces, I now need to find my standard error of b, which means I'm going to go ahead and I'm going to take that s value, 7.53, I'm going to divide by the standard deviation of x times the square root of n minus 1. So 12 minus 1. And so this is going to give me a standard error of 1.94. So now I have my bits and pieces totally together. I can now, I'm not totally together yet actually, because I still need a t star. So I'm going to do an inverse t. And we have a 99% confidence interval, so 0.005 as our area. Our degrees of freedom is our sample size minus 2. And this will give me a t star value of negative 3.17. And again, we just change that sign to positive every single time. So now we're ready to go. We take our original b value, which was 15.2. We plus or minus our t star value times our standard error. And this is going to give us a confidence interval of 9.05 to 21.35. Really big interval. Why? Because we have a really high confidence level. So now we are 99% confident that the interval from 9 to 21 captures the actual slope beta of the population regression line relating sugar level to flower freshness Last part, would you feel confident predicting the hours of freshness if 10 tablespoons of sugar are used? Well, if we look back, the amount of sugar we used went from 0 to 3. That is way above our area of study, and so we would say no. That is what we call extrapolation. Because 10 is outside our area of study. 10 tablespoons. Okay, and so next time we're going to go ahead and we're going to talk about significance tests.